All right, guys. So today I want to talk about atmospheric refraction and what atmospheric refraction would do if we were not living on a convex surface the size that the Earth is purported to be. Because there's a lot of misconceptions, I think, when it comes to refraction and what you would actually observe. Because I hear time and time again people saying, well, refraction bends light down, which means that objects are pushed up, right? That things appear higher. Well, that's only the case if you're living on a ball the size of Earth. Because if you're living on anything else, anything that's less convex than the Earth is purported to be, you would get a very different effect with refraction. So, refraction basically is when we're looking at atmospheric refraction, you have the horizon line here, and you can see that I have it oriented to where we're looking at the South Pole on the globe, right? So we're looking, this would be, looks like Australia, that area of the world. So if you're standing over here, which there's really nothing to stand on over here, but if you're over here in this vicinity, the sun is below the horizon, right? That's the point of it. And if the sun is below the horizon, and atmospheric refraction is taking place, what is happening is every time that light passes through a different medium, basically it changes direction, right? It curves down, it slows down, but it also will curve down, right? And the reason why on a globe refraction would cause the sun to appear higher in the sky is represented by this graph here. So what you see is the light of the sun is shining above the horizon, right? I mean, if the ball is below the horizon, it doesn't matter what way the angles of light are going, they're going in all directions. But it's none of the light is going to hit my eyes over here because I'm behind the obstruction, right? But if you're talking about atmospheric refraction on a ball that is the size of Earth, what would happen is that the sun would actually appear higher in the sky to an observer over the horizon because the light of the sun would be hitting their eyes because of atmospheric refraction, right? So when we're talking about refraction, when we're talking about N1, N2, the indices or the basically the indexes of refraction, different materials have different refractive indexes. Air has a refractive index. The vacuum is basically one. The vacuum is, there is no refractive index in a vacuum. But if you're moving out of the vacuum into the air, or out of the vacuum or out of the air into the water, through the glass, whatever it is, you're going to get, depending on that refractive index, you're going to get the bending of light towards the surface, okay? Now, here's where the misconception comes in. People say, well, the light is bending towards the surface, and that's going to make objects appear higher. Well, that makes absolutely no sense unless you're living on a ball, right? Because if you're not living on a ball, I mean, if you're living on a flattened out surface, and we'll just use the ball and flatten it out, I'm not going to see the ball over, I'm not going to see the sun over any horizon, right? Because the reason why this happens on a ball is because the light of the sun is able to bend down over the curvature of the Earth, right? That is why, I mean, it's counterintuitive. If light is, bending down, then objects that are, being reflected or visible because of that light in the distance would also be reflected down, right? But on a globe, those objects would be higher because of refractive index. When the sun's rays, or when the object's light is traveling, at the speed of light over the horizon, it's curving down because of refraction. Okay, it makes sense, right? On a globe, it makes sense that refraction would make objects that are over the horizon appear to be higher, right? But light isn't bouncing off of the ground and making image in the sky. That's not what the light bending down means, right? I mean, if you look into refraction, if you look into Snell's law, the reason we can see the light of the sun below the horizon is because the light of the sun is hitting our eyes, right? But if I'm looking at the light of a building across a lake, and the light of the building, because of refractive index, is curving down It's not going to be hitting my eyes if I'm not living on a ball, right? It's not going to be hitting me. It's going to be hitting the ground. And if the light is hitting the ground, what is going to happen to the object in the distance? And this is where I want to start. So I'm actually starting the entire concept of the channel over, and we're looking at it from a different perspective, because usually I like to start out with looking at the stars and thinking about the celestial motion, but I want to start with the shape of the earth, because there are so many things that are wrong with the perception or the assumption of the ball when you think about it logically. And the only point of this video, the reason why I'm starting out here, is because we need to realize that if we're going to have this debate, we need to come to a conclusion of what refraction is and what actually happens to objects that are in the distance. And what would happen on a flat surface is those objects would appear not higher but lower, because the light is being pushed down into the earth, right? Because the earth is flat. If the earth is flat, refraction doesn't make objects rise, it makes objects fall. And if that is the case, why would we ever optically measure the surface of the earth and draw a conclusion off of that optical measurement that we're living on a ball, when you can take measurements every day that don't match the ball? Right? So what do they say? Well, it's refraction, duh. I mean, the light of the sun, the reason why it appears so much higher in the sky, and the reason why these things appear to be visible from so much further than they should be, is because the light of the sun is bending over the horizon and that light is hitting your eyes. Or the light of the building is bending over the horizon and that light is hitting your eyes. But if there is no horizon to bend over, the light of the sun would be bending down into the ground, which would cause it to not reach your eyes, right? Something visible in the distance, depending on the refractive index and all of the other things that go into measuring, the so-called curvature of Earth, which we're going to go into in the next video, it is completely ludicrous to even draw the assumption that we're living on a ball with a radius of 3959. And we're going to talk about the angles of the sun, because that's what a lot of people like to say. Well, we can measure it with the angles of the sun, right? Well, no, you really can't measure it with the angles of the sun, because you're assuming that you're living on a ball, right? I mean, the angles of the sun could be a reflection. The sun could be a reflection in the sky. The sun could be a projection. Dr. Zach did a video a couple of years ago talking about the lens, right? If you put a concave lens in front of the sun, the angles of the sun are going to match, right? Well, I use a concave mirror. Same concept. If I put a concave mirror above us, like what the Bible says, what's going to happen? It's pretty obvious, right? But what I'm trying to point out, first of all, is that you cannot derive a model based on assumption from optical measurements. You really have to think about it in both ways, right? What would happen on a flat surface and what would happen on a ball? And the fun thing about it is that it works both ways, right? But we're going to get into things that don't work on the ball and can only work on the flat earth. And we're going to be talking about that. As a matter of fact, in the next video, we're going to be talking about the actual curvature over the surface of the earth per degree, right? So we're going to take the earth and we're going to make a pie. And in that pie, we're going to have 360 degrees around this circle, and we're going to figure out how much drop exists in every degree. Because the circle is congruent, right? The sphere, if we're living on a sphere, it's the same everywhere, right? I mean, people say, well, 8 inches per mile squared. Well, that's only to the observer, right? That's only if I'm standing on the ground and looking at a distance. What am I going to see as far as the drop, right? And imagine standing on a hill, a gently sloping hill. Now, you can see pretty far down a hill, right? So it's not talking about the drop. It's talking about how far you can see based on the obstruction. And I do not, the math is really janky when it comes to a ball. And it's because when you break it down into degrees, on a ball like Earth, there is no up and down, right? It's based on where I'm standing. On the ball is up, right? And the ground beneath my feet is down. So it's not up and down anywhere. And when I'm talking about drop, there's just as much drop here as there is here, if I'm talking about it per degree, right? And when you add it up, it is a very interesting concept. It's almost like the sphere itself exists in a different dimension. When you really start to think about the way we calculate the circumference, the way that we are thinking about the drop, the way that we're thinking about measuring per mile, because every mile is the same on a ball, right? And it's not 8 inches. I mean, if you're going to say that, if I go, for example, if I measure a mile and I move a mile to measure the next mile, I'm never going to get any more than 8 inches, right? And that's going to be an assumption in a lot of cases. Okay, you might get a little wave action on the water that makes it look like you're getting an 8-inch drop, but that's all you're ever going to get. You can move across the entire surface and that's all you're ever going to get. And people will say, well, it's exponential, man. I mean, the further you look, the further it drops. Okay, so here's the question. If I travel 68 miles across the surface, this is what we're going to be talking about in the next video, which is 1 degree in statute miles, about 68 miles. So if I travel 68 miles across the surface, what is the average drop per degree? And does it match the point A to point B measurement that we're always trying to use when figuring out what you should and should not see on a globe? On a globe, your curvature would be very apparent everywhere you looked because you're curving down and away in every direction. You would also see a lot further. You know, people like to pretend that there's this imaginary hill in front of you, but if you're standing on top of the hill, if you're standing on top of the ball, you can see a tremendous way. That's not going to block your view. The only thing that would block your view is like a concave surface where the Earth is disappearing into the atmosphere, right? Or a flat surface where, again, the Earth is disappearing into the atmosphere and you have a hump on this side and a hump on this side. The hump on each side, on all sides, doesn't really make sense on a ball, right? That's what we assume because we've never really been able to make a ball the size of Earth and stand on it. So we say, oh, the hump, that's what you'd see. Yeah, it's the hump. We see a hump here and a hump here and a hump there and a hump everywhere, right? But I mean, really think about it. Think about what your visibility would actually be on a ball and what it would actually look like. So the question we're going to be asking is, how many miles on average? Okay, so if you look at the circle, the drop here is the same as the drop here. It's the same as the drop here. It's the same as the drop here. It doesn't ever change on the ball. So I'll see you guys in the next video. Have a good one.